All right, so we're gonna find the area under the curve, and this is going to relate back to our integrals. So let's first talk about what the area under the curve is. All right, so first of all, we have the function f of x is equal to x squared. So I'm going to look at an interval here. I'm going to look at a to b. Now, if I look from a to b, and I look from the curve to the x-axis, I have a little region over here. And this region right here is the area under the curve. All right, so the area under the curve, it's not a shape that we recognize. It's not something we can relate it back to. But what we could do is we can take this little area here and we can break it up into equal sized rectangles. So I can go here, here's a rectangle, here, here's a rectangle, here, and my picture might not be great, but all those rectangles would have to be the same size. And if I found the area of all those rectangles and I added them together, I would get a pretty good approximation about the area under the curve, but I wouldn't get the actual area because there are little pieces here that I'm factoring in, that I'm not factoring in, I mean, when I find the area of these rectangles. But if I make these rectangles smaller and smaller and smaller and smaller and smaller and smaller and smaller, I eliminate that space there that I'm not accounting for. So let's first talk about the width of the rectangle. Okay, so the width of the rectangle is found by finding out the space between here. So if I did b minus a, that tells me how much space there is from here to here. Now, if I want to know how much each one of the rectangles are, the width of them, I'd have to divide by the number of rectangles. So if I broke this up to be 1, 2, 3, 4, 5 rectangles, I would divide by 5, and that would tell me how wide each rectangle is. But I don't know how many I'm going to put in here right now, so I'm just going to put an n representing the number of rectangles. That will tell me how wide each rectangle is. So I find the space between, and then I divide by the number of rectangles. All right, so traditionally, we would find our area by doing base times height or length times width. So if I wanted to find the area of one of these rectangles, I would need to know the base and the height. All right, so I'm going to name the width or the base of the rectangle to be this a minus b over n. And because that's constantly changing, depending on the number of rectangles, I'm actually going to use that delta x to represent the base. And then the height of the rectangle depends on the beginning point of the interval. So if I want to know the height of this rectangle, whatever number this is, if this was 1, the height would be 1 because 1 squared is 1. That would be 1. If this was 2, then the height of this rectangle here, this guy right here, if this was 2, the height would be 4. 2 squared is 4. So the height of the rectangle is, or the length, I'm sorry, is equal to f of whatever x value you're evaluating. We're not sure what the x value is. It depends on where the rectangle starts. All right, so if I want to know the area of this first guy here, this first rectangle, I would do f of x1, whatever my first x value is that I'm plugging in, times the base, height times base. Then if I want the next rectangle, I would do f of x2 times the base, height times base. And then if I want the third rectangle, I would do f of x3 times the base. And then you see each time it will get me the width, or the area, of each rectangle. Now I'm going to keep doing this. I don't know how many rectangles there are, but I know that I'm going to keep doing this, so you should notice or remember this from Algebra 2. We know that there's summing, we're adding a bunch of areas until we get to the last rectangle. The last rectangle, whatever that number is, I don't know what it is, but I'm going to plug it in. The last rectangle's height times the width. So if I want the area under the curve, I would add up all those little individual rectangles and I would get the area under the curve. All right, so that's a summation. If I add up all of these guys, I'm taking the sum of each height times its base. I'm going to start with the first rectangle, and I'm going to end with the last rectangle. Remember, n was the number of rectangles. And I want to have a lot of rectangles because I want these rectangles to get super skinny so that I'm pushing the shape closer and closer and closer to a straight line as possible. So what I'm going to do is I'm going to take the limit as the number of rectangles goes to infinity. So I'm going to send the number of rectangles to be infinitely many rectangles, and then I'm going to sum all those rectangles. This is the area under the curve, which by definition is our definite integral of a to b of the function dx. B is the number furthest to the right in the interval. Now to find the definite integral from a to b of f of x dx, what we do is we integrate, because that's what the integral means, and then we evaluate. We evaluate, the capital F represents the integral. We evaluate into the integral, b. We evaluate into the integral, a, and we subtract it. So this is the integral of little f of x. Okay, so this is sort of like a formula that you need to know. Definition. All right, so now let's use it in a concrete example. Okay, and the gist of this is a bunch of rectangles, make the rectangles super skinny, and then add them all up. Okay, so we're going to find the area under the curve of f of x is equal to x squared from 1, 2, 3. All right, so the first thing we're going to do is we're going to make the definite integral. So the definite integral looks like this. X squared dx, because the function is x squared, from 1 to 3. 1 to 3. Okay, so now we're going to integrate this. So to integrate this, we add 1 to the exponent, and then we divide by it. Add 1 to the exponent, divide by it. Now we evaluate the integral from 1 to 3. Notice that it changed from an integral to these squared off brackets, and now we're going to evaluate. So I'm going to put in the b value first. That's the end of the interval. So 3 to the third over 3. And I'm going to subtract it by putting in the a value, which is the beginning of the interval. 1 to the third minus 1. So I just put 3 in here. I put 1 in here. And now I'm going to evaluate. So 27 over 3 is 9. 9 minus 1. So the area under the curve is 8. So what that means is if we looked at a picture of x squared, which we looked at before, it looks like this. If we look from 1 to 3, and we looked at just this section over here, this would be 8 square units. All right, so now let's talk about this for a second because we have to be careful when we talk about the indefinite integral, the definite integral with respect to the area under the curve. The definite integral gets you a signed area. And what a signed area means is if you're completely above the curve, like in this example, I'll give you the 3 cases. If you have a curve and you're completely above the x-axis, if you're completely above the x-axis, and you take an interval, and you look from here to here, if you take the definite integral from a to b of f of x dx, this is f of x here, because it's completely above the x-axis, you're going to get a positive answer, which is going to actually give you the exact area. If you have an f of x that is completely below the x-axis, and you took the area under the curve, it's not really under because it looks like it's above actually here. It's always the x-axis to the curve. If you took the indefinite integral here, because it's completely below, you're going to get a negative number. Now, we know that area can't be negative. That's why we say it's the signed area. Because if I want the actual area of this little orange section, I'd have to take the absolute value of my answer to get the actual area. Okay, so that's the second situation. So you're completely above the x-axis, you get the actual area. Completely below, you get a negative area. And if you want the actual area, you have to take the absolute value. So if you took the indefinite integral here, you got negative 10, you would say this area here is 10 square units. Okay, the last scenario is when you have a function that is above and below. So this one's tricky because if you look from here to here, this is going to give you, if I took the integral, we'll call this point C, from A to C, if we took the integral, we're going to get a negative number. And if we took the integral from C to B, we would get a positive answer, the actual area of that little section. So when we take the integral from A to B, the whole entire thing, it's going to add up those two areas. So you're not getting the actual area here. You're getting the net area because one of them is going to be negative. So this is not going to give you the actual area because this will be negative, this will be positive. So say this was negative 10 and this was positive 10. You would get an answer of 0, which is possible for the definite integral, but it's not possible for the area. So you only get the actual area. You only get the exact area when using the definite integral if the interval they're giving you is continuous and f of A through f of B is positive or above the x-axis. All right, so watch the next video to see how we can use the indefinite integral a little further, and we'll keep working on this.